Coming back to the closed loop, the first point in the battery cell is the chemistry. I'd like to welcome Frank Blume on stage. Please, Frank.
Thank you, Thomas.
Frank, before I hand over, promise me to make it not too complicated, please.
I will try.
Thank you.
I will do what I can. Thank you, Thomas. So let's get into the inside of the battery cell. That's the chemistry, basically. We do have an entry chemistry with iron phosphate. On a long-term base, we see high manganese content for the volume vehicle segment, and for specific solutions, high nickel, manganese, and cobalt is important because high nickel means high range, high performance. The end game, out of our point of view, is solid state. Before I get started, I have to explain a bit what a lithium-ion cell is. We see the anode, very simplified view, a separator, the electrolyte, and the cathode. The anode drives the charging very much. The cathode drives the range and the cost of the battery cell and the battery systems very much. Let's get to the cathode. The cathode is the control lever for sustainable supply chain, cost, and range. Here we see the state-of-the-art technology. The chemistry today, typically used in all electric vehicles, is nickel, manganese, and cobalt. That defines the cost of the cell by 40%. I don't think there's any other layer into the car what defines cost that much. And also the range comes out of the cathode by 90%. Getting to LFP. LFP has a big cost advantage, a slight range disadvantage. Iron phosphate, that's LFP, comes without any cobalt, nickel, and manganese, and is a very robust technology. The cycle stability is very good. That means especially for cars with low range, this is a very promising technology. High manganese cells. That's a long-term, out of our point of view, very promising technology because it's cheaper. Nickel content is lower. Nickel is quite expensive. Cobalt is too. There's no cobalt any longer in the cell. And the range is on the same stage than the cells today, the state-of-the-art technology. Let's get to the anode. As said, the anode is the control lever for charging performance. If the anode is charging, all the lithium has to go into the anode. That's why it's 100% performing the charge time, the charge performance. The anode also has a chance to improve energy density and with that range by 10%. And that can be done by synthetic graphite plus silicon. If we get silicon into the anode, we have a better range. It's plus 10%, and the charging time performs better too, because the silicon can connect more lithium ion than just the graphite. We do have it in production. The Porsche Taycan and the Audi e-tron GT are using that already, and they are the benchmark for charging time in these days. Now I'd like to talk about solid state. Again, this is the end game for battery, lithium-ion battery cells. The simpler design leads to higher performance and lower costs. We start again with a more concrete sketch, a more detailed sketch of anode and cathode. So the anode content is copper and graphite, separators in between, electrolyte is there, and it's fluid electrolyte to make sure the lithium ion can move between the two parts. Cathode is on the other side, content in this case is NMC and aluminium. Coming to solid state, here we see that there's no graphite any longer, no liquid electrolyte. Separator is the key of success. That's containing the solid state technology, making sure that the lithium ion can go in one and the other direction. And with that, we have an improvement of weight, of cost, and of charging time. There's no barrier any longer as graphite or silicon for charging. And only the anode today in an ID3 with the biggest battery is 100 kilogram. We can get rid of that weight too. That means the charging time can be less than a half compared to state-of-the-art technology, and the range will be plus 30% because the cell has less weight, is easier and simpler. I want to prove that with data. Here we see data from our partner QuantumScape. The solid-state battery will come in now, and you see that a solid-state battery, as we have it now, and a 10 to 80% is a typical charging with high-performance charging. Here we are at 12 minutes already. That's a proof of concept for the technology. A standard state-of-the-art cell today is between 35 and 20 minutes. So faster is always better. That's a big thing we made here with our partner QuantumScape. And of course, there's still a lot to do to industrialize the technology, but the proof of concept for the design we see already here. What does that mean in reality? In reality, we just took out a few examples, 450 kilometer or 280 miles range from Los Angeles to Las Vegas, for example, Leipzig to Munich, or Beijing to Dongying. And that has to be done today with a charging time of 25 minutes. 25 minutes is not too bad, but we are planning to get to 17 minutes until 25. And with solid-state technology after 25, we are able to do it in 12 minutes. So that's a big advantage and will help the customer to adapt the technology also to long-distance drives. Now I want to come to race applications for lithium-ion batteries, and it's my pleasure to hand over to Oliver Blume.